found all the asymptotes. We found the x-intercepts. Kind of figured out what they look like on the graph, but we didn't figure out what goes in between, and this one had a lot more happening. So I wanted us to get a chance to look at that. So what was our vertical asymptote, or asymptotes in this case? Okay, so we got x equals, what was it? 0? I don't think 0. I don't think for vertical asymptotes.
Oh, that was, sorry, x equals -1/2.
Okay, x equals -1/2, and x equals, what else, 3? Okay, that came from factoring the denominator, which we had factored out yesterday, and then setting those factors equal to 0. Our horizontal asymptote, 3/2. Okay, so remember we took the coefficients. We took the coefficients because if we multiplied each polynomial in the numerator and the one in the denominator out, they would both be x squared, the numerator with a coefficient of 3 and the denominator with a coefficient of 2. All right, and then what were our x-intercepts? 0, and what else? Okay, and that came from setting the numerator equal to 0. Each of those factors gave us 2, and remember, these are points. These are not asymptotes or equations of lines, and so that meant we had a point here at 0, 0, and a point at 1, 0. Stop distracting people. All right, so we talked about how the vertical asymptote splits up the graph. The horizontal asymptote helps us at the ends. Okay. Okay, so the horizontal asymptote is just helping determine end behavior. The vertical asymptote is there to literally partition your graph into separate branches of the graph. Okay, so here's this partition at -1/2. Let's think about what we think is going to happen to the left over here. Okay, did you guys already write down what happens to the left? Yeah. Okay, and where did our branch end up? In the top left. How are a couple ways that I could figure out that it ended up here? Okay, so one way is with our little sign chart. Okay. If we're thinking about the x-axis and the places it's split up by asymptotes or by intercepts, we have -1/2, 0, 1, and 3. And we got a positive when we looked at our function if we were plugging in a negative number. How else could you have known that that branch had to go up there and not below the asymptote? Good. There's no x-intercept here. And if this graph had gone below the asymptote, it would be expected that it would cross the x-axis in order to follow the vertical asymptote, and you would need another x-intercept there, and we don't have one. Okay. All right, what about the far side past 3? Where was our branch? Above or below the horizontal asymptote? Again, above. Okay. And again, that could have been for one of 2 reasons. One, we checked the sign chart, okay, which is how we'll know for sure. But we also should have been able to predict that again because there's no x-intercept here, so I wouldn't expect it to cross the x-axis, which it would need to do if it was on the other side, below it. Okay. All right, so what's happening in the middle? So again, if we look at our function, and we had written it in factored form to help analyze it a little bit. So we have this 3x, x minus 1, 2x plus 1, and x minus 3 in the denominator. So what we had been doing with our sign chart was plugging values in kind of a certain range of x and seeing what would happen. Would we be above or below the x-axis? So the next range of stuff we have to look at is this very small range right here between -1/2 and 0. So what's a number you could think about if you wanted to think about a specific number in there? -0.25 or -1/4, okay, if you have to. Now, some of it you don't really have to. If you're plugging in something between -1/2 and 0, this right here, this factor, negative or positive? Negative. Positive times a negative, negative. What about here? A negative minus 1. A negative and then take away 1. Still negative, right? And a negative, take away 3. Negative. The only thing that might be a little more confusing is what happens here, so we could actually think it through. If we were using -1/4, what is -1/4 times 2? -1/4 times 2. a negative 1/2. So we have a negative 1/2 and a positive 1. Is this going to turn out to be positive or negative? Positive, more positives, okay? All right, so 2 negatives in the numerator mean the numerator is going to be positive. The denominator is going to be negative, and the positive numerator divided by the negative denominator will be negative overall, okay? So that means I expect it to be following this asymptote and cross through that x-intercept, okay? And then let's look at what happens between 0 and 1. So does it turn around at that point, or does it go up through it? So 0 and 1 would be like plugging in positive 1/2. So what's going to happen to this factor, 3x? Positive? What about like 1/2 minus 1? Negative. 1/2 times 2. Well, we'd be plugging in a positive here, so how's it going to turn out? Positive. And 1/2 minus 3? Negative. So in the numerator, we have a negative when those got multiplied together. Same in the denominator, and a negative divided by a negative overall will give us positive. So I expect it to go kind of along the asymptote up through that intercept. Be positive up here. I'm kind of expecting negative back through the other intercept because I know it's positive, but it's got to come back to that intercept. Okay? So we'll see if my expectation ends up being true or not. So then between 1 or 3, think about plugging in like the number 2. Here this would be positive. Here this would be positive. Here it would be positive, but here it would be negative. So overall, what are we going to get? A negative. So I'm expecting that in here something like this kind of deal is happening. It's not exactly parabolic with the way the intercepts are and stuff, but something like that where it's turning around, since it was below, above, and then back below in between that area. Is this okay with what we were talking about yesterday? So we find all of this information first, we put it on the graph, and then we use kind of the signs above or below the x-axis to help us determine where the curve will go. You don't actually have to plot any specific points except for your x-intercepts. Okay. You okay with this? All right, so what's the one thing that we don't know how to find yet or haven't talked about? Holes. Okay, so today our focus is going to be on finding holes. So some people stated that in the homework, they couldn't do the homework because the directions said, oh, go find the 5 things that it said and whatever. Look at your assignment sheet. Your assignment sheet says, find vertical asymptotes, oblique asymptotes, horizontal asymptotes, x-intercepts, holes, which we're going to talk about today, and then graph it and find the domain and range. Do those things, okay? Whether you have the book to look back at the 5 things it says to find or not, those are the things that you're finding, those same things that we've been concentrating on over and over again, okay? All right, so what's it going to look like when we have a hole? All right, so here we have a function, okay? We look at the function. We're going to find out all the normal things that we would find out, but there's something special about this function that creates the fact that it does have a hole. Does anybody notice something about this function different from some of the other ones we've talked about that would cause this idea of a hole? Okay, we can factor. We could factor in the last one, the denominator factored also. Okay, good. But in this case, once we factor, they cancel out. So notice that if you write it in factored form, this factor cancels out, making our function a lot simpler. What is it going to look like if I just graph this part right here? A line. Okay? So that's what's happening. But you can't ignore the fact that if you had taken the original problem, could you plug -2 into the original problem and get an answer? If you plug -2 into the original equation, what do you get? 0 over 0. What is that worth? What's 5 over 0? Undefined. So 0 over 0 is not defined either. How do you define it? Well, when we divide things by 0, they're undefined. Usually things divided by themselves are 1, but 0 divided by anything is supposed to be 0. So there's like 3 properties that could apply to that number. None of them actually quite fit, so that is another undefined scenario. Okay? So here's the problem. It boils down to a really simple graph for us, which is good. But we can't ignore the fact that in the original problem, we couldn't plug in -2. Can we plug -2 into this and get a solution? Yeah, we plug in -2 and we get -4. Does the point -2, -4 really exist if you are really graphing that equation? If you plug -2 in the very original equation, do you get -4? No. So here's what you're allowed to do. You're allowed to simplify it and graph this one instead. But there will exist a hole, okay? The hole is going to exist because these factors canceled out and because of the thing that we just talked about. If I look at plugging -2 into the new function, I feel like there should be a point on my graph that would be -2, -4. But if I plug -2 into the very original equation, I get something undefined. Everything else you plug in will work out just fine and dandy. Think about plugging in 1. If you plug 1 in here, what are you going to get? -1. Now go up there and plug 1 in. 1 minus 4 is -3. 1 plus 2 is +3. -3 divided by +3 is -1. The same thing you got here. Every point is going to work out to be the same because it's the same function except for this right here. Okay? So because of that conflict, we say you're allowed to graph this function, but because there was a denominator of x plus 2, that means that you have a hole. Okay? So if your denominator gets canceled out, yay for you, something simpler to graph, but you need to put a hole in the graph because of this conflict of information, the one piece of information that doesn't match from the original equation to the new equation. So if this is a line, do we have a horizontal asymptote? Does it even out and just go flat? If this is the line you're graphing? What does this line look like on the graph? Think about it. Okay, so Ryan's going like this, right? Has a positive slope. Is it going to flatten out and be horizontal? No. Okay, so no horizontal asymptote. That makes sense. Look at the original equation. Which one has the higher degree, numerator or denominator? Numerator, okay. Which means normally then we go and look for an oblique asymptote, okay. Well, what happened when we divided those things out? Well, it just simplified to this, right? So basically it is its own oblique asymptote. Remember the oblique asymptote was supposed to be like the line that it followed at the end? Well, it literally is the line. So if you had to list one, you would just list itself. Okay, it follows itself, right? Okay, what about vertical asymptotes? If you looked at the function originally, what would you think is the vertical asymptote? X equals -2. But that got canceled out so that we just have a line. So we don't have any vertical asymptote. But we can't forget that we canceled out a factor. And because we canceled out the factor, we have to consider this idea of a hole. Okay? So the hole is at x equals -2. So it doesn't mean it's the line x equals -2. It means wherever on the graph you would get the point where x is -2 and the points wherever it's at, there's just a hole right there. Okay? So it means this. Let's go and graph this line. So y-intercept of -2, slope of 1. I can't draw straight lines, so I have to do this. Okay. This would be the graph if no hole existed. Okay? But there is a hole. Where's my hole? At x equals -2. Now that does not mean it's this own little thing floating off in space by itself. It means the point on the line when x is -2 does not actually exist. So it means when x is -2, I thought that it crosses through -4. Remember how we talked about this? This equation says at -2 it would be -4, but the original equation says at -2 it would be undefined. So this point at -2, -4 doesn't actually exist. Okay. There is literally a hole there. Okay? So it's like the line goes, skips this one little point, and then just keeps going forever. All right, so somebody tell me, how are you going to identify when there's a hole? You're going to look at your equation, you're going to start working with it. What's going to be your red flag? Like, oh, this one has a hole. Caitlin? Good. When you can factor and cancel something in the denominator. Now, if there was more than one factor in the denominator and one canceled out and one didn't, the one that canceled out is a hole. The one that didn't is going to give you a vertical asymptote, right? Okay, because normally stuff in the denominator gives you vertical asymptotes. But when something cancels out, that means hole. Graph your final answer first, then go to the point on the graph that you know should not exist and make it a hole. Okay? All right, I guess we also have to list X-intercepts. This being a line is a little bit different than some of the other stuff. What is the X-intercept to? Good. Which, notice, is just the single X-intercept that's left after you simplified. If you set the numerator equal to 0 originally, you would have got +2 and -2. But at -2, there's actually a hole in the graph, so there's no X-intercept. So think about it when you're done. Yeah. If I plug -2, so I focused on -2 because -2 what is the X value that would have made the denominator equal to 0. Okay. So then I thought about when I plugged -2 in here, what does it appear like I get? Well, when I plug in -2, -2 minus 2 gives me -4. Okay. All right. Questions? Okay, what about domain and range of this graph? What's domain? All real numbers except -2, so we can just say x cannot equal -2. And what about the range? All real numbers except -4, right? Because of our stinking hole right there. Okay. So y cannot equal -4. So any questions? All the other parts are going to be the same. Yeah.
So will they only always that number?
Yes. The hole is always going to be at the x value that would have made the denominator equal to 0 originally, but now is no longer in the denominator. Okay? So if the original function had a factor in the denominator that got canceled out, the hole is whatever x value would have made that original denominator equal to 0 that is no longer there. Okay? All right, we'll do one more that has a hole. All right, so even if we didn't know we were looking for things with holes, you would want to factor the denominator originally, because if you were looking for vertical asymptotes, you'd also want to see the separate factors to see where those are. So I'm going to go ahead and take this function and factor. And then I'm going to notice that these cancel. So when I'm graphing, I'm really going to focus on graphing this. Oops, not that. Okay. So I'm going to focus on graphing 1 over x plus 3. So everything I do is going to be about 1 over x plus 3, except for the fact that I canceled something out, so I have to be aware there's a hole. But my whole graph that I'm going to build and all this stuff is going to be focused on the normal procedure that I would use to graph what's left right here. Okay? The only thing that this tells me is that since a factor canceled out in the denominator, I have a hole. Where is my hole going to be at? At what x value? Okay, good. So I hear votes for -3 and for 5. Those both serve an important role, but which one is actually the hole? So which one was canceled out? Yeah, the x minus 5 factor. So your hole is at the x value that the one that canceled out would have been. Okay? So the whole is the one that is no longer there, okay? The 5. What is negative 3 going to do for us? Good. Because now I'm going to graph this according to the normal procedure I would graph it. At the end, I'm just going to make sure that at x equals 5, there's a little hole in my graph. Like instead of curving, it like skips one little piece. Okay? So this I'm going to graph like normal, which means my vertical asymptote is going to be at x equals negative 3 because I get that by setting what is left in the denominator equal to 0. What about horizontal asymptote? You're looking at your new, nicely simplified function and doing all the things we would have done with it yesterday or the day before. Just at the very end, we're going to put in a hole. So what's the horizontal asymptote? Y equals 0. Good. Okay, because who has the higher degree, numerator or denominator in this case? Denominator, right? We're looking just right here. This has degree of 0. The denominator has degree of 1. When the denominator has the bigger degree, your horizontal asymptote is automatically at y equals 0. Okay. So because there's a horizontal asymptote, I don't have to go looking for an oblique asymptote. So I've covered vertical asymptote, horizontal asymptote, oblique asymptote. I already marked a little thing for me to remember about my holes. And then x-intercepts. So remember, we're looking at this function. Okay? All of our graphing can be done with this function. We just have to remember this one little fact about putting in a hole for the original way it was built. Okay? So in this function, what are going to be our x-intercepts? Let's go back to how do we find x-intercepts? Good. Okay. Find the x-intercept of anything, you set the y equal to 0. So remember that looked like this. And for us, with these functions that are built like fractions in this unit on rationals, that really means the numerator gets set equal to 0. But can we change our numerator? Does it have a variable in it that we could plug stuff in for? No, it's 1, which means it can't equal 0, which means there will be no x-intercepts. Okay. So again, just want to emphasize that the new thing here is that we canceled out this factor, which we're making a note of. It's going to make a hole. But all this stuff that we're talking about for this function is the same stuff we reviewed yesterday and the day before. Vertical asymptote, set denominator equal to 0. Horizontal asymptote depends on who has the higher degree, how you make that decision. X-intercepts, setting the numerator equal to 0 if possible, but when the numerator is constant, we can't really get any x-intercepts. So we have this graph. If we were going to graph this normally, okay, if we were just graphing this and we didn't even know this whole part existed, we would then go ahead and think about our little sign chart, and our only separation is happening at negative 3. So if you plug in numbers to the left of negative 3, so like negative 10, negative 100, negative 1,000, what's going to happen to the value of the function? Negative or positive? Negative, right? So because the numerator here is always positive, it's just 1. So if you plug in anything negative here, whose numerical value has more than 3, it's going to end up being negative, giving this negative. Now when we plug stuff in that's bigger than negative 3, positive numbers, negative 2, negative 1, is the denominator going to be negative or positive? Positive, making the value of the whole function positive. So what I expect is, on the left side of my vertical asymptote, I expect everything to be below the x-axis, whereas on the right side, I expect everything to be above the x-axis. So given the asymptotes as our guideline to draw the curves, I expect this, and I expect this. Actually, I'm going to draw this out a little bit longer. All right, so I graphed this function. What's the one thing I have to represent on my graph back from the beginning, that I have to go and consider? The hole, okay? So So I graphed this, how it should look if this was the given function, but really my given function was this, so I have to account for the fact that there's a hole at x equals 5. So the question is, where is that? So 1, 2, 3, 4, 5, somewhere right here. And if you're not sure exactly what value it is, okay, like the hole is at 5, comma something, that something is what we would get when we plugged 5 into this function. What do we get when we plug 5 into this function? 1/8. So there's my hole at 5, 1/8. Okay. And clearly it's hard for you to tell whether mine's at 1/8, 1/4, 1/2. It would be hard for me to tell yours too, as long as it's in kind of the general right location. All right, so all the things that we found, vertical asymptotes, horizontal asymptotes, obliques, if we need them, x-intercepts, holes. Because it's at the x value that would have made the original denominator equal to 0. Does that make sense? All right, domain and range for this graph. So what is the domain? Okay, so all reals. Are there any exceptions? 5 and -3. So our vertical asymptote is causing an x value we can't plug in, and our hole is causing an x value that we can't plug in. So the graph literally like skips over those x values. So our domain could include anything except, or x cannot equal, -3 and +5. Okay, what about our range? The y values. So it shoots forever up and forever down. What are their gaps? 0 and 1/8. You guys understand why Ryan's saying that? So 0 because of the asymptote, so we know it never quite reaches that at the end. And 1/8, all the values it's going to hit right here, it's going to jump over 1/8 and then continue hitting the other values. So either all real numbers except for 0 and 1/8, or just say y cannot equal 0 or 1/8.